Current long-range planning for space exploration is focused on a single destination, placing human boots on the surface of Mars. A mission to Mars requires a 2 to 3 year commitment. Because of the way orbits align, there is no quick return option if a crisis occurs. Once the transit begins, the crew is committed to the full duration of the journey. Compare that to low Earth orbit. Aboard the International Space Station, astronauts are suspended just above the atmosphere. Returning home takes only a few hours. This illustration shows the environment waiting beyond our planet's magnetic shield. Deep space exposes astronauts to intense, unshielded solar radiation and solar wind that can cause acute health risks over a multi-year mission. Because of these hazards, we cannot make the leap straight to another planet. We first have to build a testbed, an environment just days away from Earth, where we can develop survival strategies needed for deep space conditions. This graphic maps out that transition. The Artemis program serves as a proving ground where we can test our hardware and refine survival protocols at the Moon before moving to the Mars-ready phase. Escaping Earth's gravity with heavy, deep space payloads requires a new class of launch vehicle. This is the Space Launch System, or SLS. Once the SLS breaks orbit, the astronauts rely on the Orion crew module. It is a specialized vessel designed specifically for the navigation requirements and life support needs of long-duration missions. The Orion capsule is physically attached to the European Service Module, which provides the critical power and resources for the entire ship. Looking at this diagram, you can see the international distribution of the hardware. This single module provides the crew's propulsion, drinking water, breathable oxygen, and thermal control. This interconnected architecture makes the Artemis program an international dependency. By distributing the development of life-critical components across multiple space agencies, the program relies on a globally integrated supply chain to function. Before attempting a lunar landing, NASA must verify this hardware in the vacuum of deep space. That is the objective of the Artemis I and II test flights. This map illustrates the flight path for Artemis II. It follows a hybrid free return trajectory, a figure-8 pattern that loops the crew around the Moon and back toward Earth. During the outbound journey, highlighted in yellow, the crew executes precise trajectory correction burns with their auxiliary engines. These maneuvers are required to aim precisely for the Moon's gravity. Following the purple line back, the crew enters Earth's atmosphere at 24,500 miles per hour. At Mach 32, the heat shield must withstand temperatures that exceed 5,000 degrees Fahrenheit, the highest re-entry speed ever for a human-rated spacecraft. These orbital flights act as dress rehearsals. By verifying the underlying physics and hardware safety in a deep space environment, we establish the mission parameters needed to support a human surface landing. This timeline shows where the program's focus shifts. Starting with Artemis III, the goal moves toward establishing a permanent, sustainable infrastructure in the lunar environment. A central part of that infrastructure is the Lunar Gateway. It is a staging point orbiting the Moon, serving as an outpost where spacecraft can dock and resupply before astronauts descend to the surface. Surface operations at the lunar South Pole will eventually include permanent habitats and pressurized rovers. These tools allow astronauts to navigate the harsh terrain and conduct long-term research. The combination of the orbital gateway and a surface base allows humanity to maintain a continuous presence off-world, shifting our capability from temporary visits to sustained habitation. It is easy to view the Artemis program through the lens of the historical Apollo missions. But where Apollo was a series of short-duration landings, Artemis is the development of a permanent operational foundation. Mastering resource extraction and radiation shielding on the Moon is a technical requirement for reaching Mars. By building these systems now, we develop the expertise needed for longer voyages. The next time humans leave footprints on the lunar surface, they will be marking the location of a permanent base. These missions establish the foundation required to support humanity's expansion into the solar system.